Technicalities. I'm amused, so I win. But it's like, you know, if it's everybody who wins gets an A, everyone who dies gets a B, at least the people who die have some incentive, you know, like, want that grade boost.
What if you're like top 5 you get a B plus or something? So you get incentive to live a little bit longer.
I just don't know if I'm not feeling that lenient. No effort, you get an F, and you die.
You give an effort. You give an effort to live to the top 5. So 15 other people die before you.
You die with a great GPA. There you go. I think B plus is valid there. All right, so if we did have a death match here, who would win?
No. Yeah. Ultimately. Sneak up from behind.
Too bad I know you're behind me. I'll just turn around.
Like how Vince, problem is, I wouldn't. I don't think I could kill anybody. I've punched one person in my life, and it was my brother. Once, like in elementary school, I had a kid come up to me and just punched me as hard as he could in the stomach. And I just sat there and watched him. I had another kid come up and do that whole, like, right in front of your face, and then he actually just, pow! And I just started crying, and he's like, don't tell the teacher. And I'm like, I won't, man, I won't. No, I didn't. I was that kind of kid. Like, you can punch me in the face, and I'd be like, whatever. I mean, I'd cry because it hurt, but yeah, although that kid, I ran into him last year, and then he got arrested in my neighbor's backyard, being both high and drunk on a lawnmower. So that was interesting. Yep. Well, he ran a lawn service, but he was like super high on drugs. So welcome back to class. I just put all of that on YouTube. Yep, this microphone's on.
Administration to be like, all right, let's check on the
I've heard he's a pretty good No. Oh, heck no. All right, so in more professional terms, now I will not smile or laugh for the rest of this class. So, in the previous class, we have learned about the R, L, and the C circuits. Okay? And what we learned about was the value of zeta. So we're going to do it again. So it'll just be a short example to show you a different instance of that exact equation and methodology. I gave you this circuit last time. Now, the equations that I gave you are no longer valid for this system. And the reason for that is because things are a little different. Instead of everything being in series, which you can rearrange them in series, and it doesn't hurt anything, you can rearrange components in parallel. But for this series, I can't take a component in parallel. I can't switch my inductor and my resistor and get the same circuit. It actually changes substantially. For that other circuit, if I changed all three of my components around, it changed nothing. Here, because these are in parallel, and this is in series with these components in parallel, I can switch these two, and that causes no problems, because they're just both in parallel. I can put this down here instead, and that has the same solution. That doesn't change anything. But I can't put my resistor in parallel, because it's not in parallel with my system. That would actually create a very different system. So here, this is fairly unique. We're going to go ahead and step through the solution method for this problem, just because I want you to have a little bit more exposure to how to solve more than just one problem. One problem is great, 2 problems is better, and quite frankly, you're never going to solve a very complex RLC circuit. Even those of you who are going into the electrical engineering field, it's just you don't solve more complex than just one resistor, one capacitor, one inductor, or maybe you'll come up with an equivalent capacitance or inductance. You just don't do it usually. The math is gross, and there's computers that can do stuff for us. So here we will say Vs, we'll give your component values. Vs is going to be equal to 24 volts. Your resistance is going to be equal to, we'll say 50 ohms, just for funsies. Your capacitance is going to be equal to, you know what, we'll make that 1 farad, just because it's friggin' huge. Okay? And then your inductance, we'll say that's 10 henries. Okay, so step 1 is drawing the circuit. What's step 2? KVL, KCL. And coming up with our component equations. So step 2, we've got how many loops do we have in this system? We got 2. I mean, we could have 3 if you want to include this as a loop, but it's redundant. So we'll say loop 1. We'll say loop 1 is this pane right here. What equation do we have for loop 1? Okay, loop 2, what equation do we have? Nice work. And then if we did a loop 3, which is the one over here, we would just get the equation that VL equals VR. Nope, VC. Okay, so we've done KVL. Now what do we do? We got to do KCL. Okay, so what is KCL? How many nodes do we have? We got 1, we got 2, we got 3. You are on your game today, Dylan. Nice work. So at node 1, what's our KCL equation? Okay, what about at node 2? Okay, and then what about node 3?
Just IC plus IR.
Okay, now what? Now we have to write down our component equations. Okay, so for our component equations, we got 3 of them. We have VR equals IRR. We have VC equals Nope. IC is equal to C dVC dt. And then we have VL is equal to L DIL dt. Okay? Nothing we haven't seen before. Now what do we do? What? We start building our constitutive equation. So, okay. Switching markers. Huh? No, I'm just trying not to laugh. The problem is if I don't laugh, I cry. So, okay, how are we going to start with this equation? Let's say we're going to try to solve for IL, okay? Because we solved for VC last time. Let's try solving for IL this time. So you're saying loop number 2 equation? I'm saying loop number 2 equation. That's what you're saying. Because the thing is, the first equation you pick to build your constitutive equation from, you want to have your forcing function present. So we'll start with equation number 2. Vs is equal to Vr plus Vl. Okay, you wanted to start from here, which would cause some problems because we don't know what IR is. We'd eventually have to loop out and we'd have to get it into V. Yeah, we would eventually have to get it into the form of Vs. So just gonna go ahead and short circuit everything and just pick Vs. Okay, so what do we do to this? What other equation has Vr in it? We always go to component first when we build our constitutive equation. So this becomes IRR plus, what about VL? What other equation has VL in it? Okay. Now what can we do with IR? What equation do we have that has IR in it? We're good on this one. We got it in IL, we're good. What do we do with IR? Huh? Okay, we can plug in this one. So Vs is equal to IC plus IL times R plus L DIL dt. Okay, now we got an IC in there. What can we do? What other equations do we have that has IC? We got this one. So Vs is equal to C dVC dt plus IL times R plus L DIL dt. What equation do we have that has VC in it? We got this one, loop 3 equation. So we can just directly replace VC with VL. So we have Vs is equal to C dVL dt plus IL R plus L DIL dt. Okay, we got one more variable that we don't know. This has got an IL in it. This has got an IL in it. This one's just VL. What do we do to turn VL into IL? We use this component equation, which is the relationship between the voltage and the current. So, our constitutive equation is Vs is equal to C L d squared IL dt squared plus IL times R plus L DIL dt. Man, that's gross. That is super gross. This is the grossest thing I've ever seen in my life. All right. You know what? I'm going to clean that one up. I don't feel right about that. You are just too nasty. Get yourself under control. So we got Vs divided by RLC. Because we got an R, we got a C, and we got an L. Did I make a math error there? No, I'm good. I'm good. We're good. Yeah, we're good. Is equal to d squared IL over dt squared plus 1 over LC. Nope, that's this component here. This is R over C. No. 1 over RC. My bad. DIL dt plus 1 over LC times R. No, that's not an R. that's an IL. My bad. There we go. Okay, so this component, I divided everything by RLC. And the reason why was because I'm trying to get all of the coefficients out from the front of our double derivative. Okay? So there are no coefficients here. The coefficient is 1. Here, I divided this by RLC, which means RC goes on the bottom. This, I divided it by RLC. It was just R times IL, so you get LC on the bottom. Okay? Now what I'm going to do is the same thing we did last time. We're going to take this equation and we're going to transform it into some kind of a forcing function is equal to d squared IL over dt squared plus 2 alpha DIL dt plus omega naught squared IL. You will notice we have a different equation. Alpha and omega naught are going to be different values. Why? Because we friggin' solved the circuit, doing everything right. Once we get to this point, the solution method is now the same as what we did You okay? Charlie horse? You just bang your knee? Okay. Hey, I gotta check on your well-being during class. I'm over here torturing you, but I mean, it's not your job to do that for me. You take the fun out of it. So we have to figure out what alpha and omega naught are. Okay? So there's a 1-to-1 here. Here we know 2 alpha is equal to 1 over RC, because that's just, we're taking the coefficients and setting them equal to each other. And we also know that 1 over LC is equal to omega naught squared. So what is alpha? What? It is 1 over 100. Alpha is equal to 1 over 2 RC, which if we plug in the value for that is equal to 0.01, as Dylan pointed out. Okay? What is omega naught? It's 1 over the square root of LC, which is 1 over the square root of 10, or the square root of 0.1, which if I pull out my calculator, is 0.316. Okay? What is zeta? What is the formula for zeta? Alpha over omega naught. We figured out what alpha and omega naught are. How did we do that? How did we figure out what alpha and omega naught are? Math. I mean, yes, but what did I do to figure out alpha? What were all the steps leading up to, here's the equation for alpha? Somebody explain it to me. Yep. So the idea is, to get to this point here, you have to figure out your constitutive equation. You have to then force your constitutive equation to have this form by setting your coefficients equal to each other. Okay? Once your coefficients are equal to each other, then you have it in the same form, and that's where we are here. Have I lost anybody yet? If I gave you a different circuit and I asked you to solve for what alpha and omega naught are, could you do it? It's all Caden's very confident. Could you do this, Igor? You give me that look. Do you need me to go back and explain how we got here? Do you want me to? We're here. We're all together. If you don't know how we, oh man, I should remove this monitor. Just make life easier for you. Yeah, it's not the monitor that's causing it, it's the math. Okay, let me go through this one more time, just because this is important information. The way that we get alpha and omega naught for a second order system. First of all, you draw your system. That's step 1. Step 2, we write out all of our equations. Step 3, we then combine our equations to find one variable. That variable is either IL or VC. You do not solve for any other variables. I mean, you can, but you're going to find out why I told you not to do that. I have not made you do that in this class. I don't want to waste time. So once we do that, then we're solving for the constitutive equation, which is we have a forcing function on one side. We have our variable on the other side, okay? So we end up with this. And then what I do is I try to get it into this format. So I divided everything by the coefficient that's in front of the square, because that's 1. So we get to this format where now we have a 1 here. Then we have a 2 alpha, where 2 alpha is equal to 1 over RC, because those are the coefficients in front of the derivative. 1 over LC is equal to omega naught squared, because that's a coefficient in front of IL. 1 is equal to 1. And here our forcing function is equal to VS over RLC. Okay? So we have put this into this format. we take our formula here because we know 2 alpha is equal to 1 over RC, solve for alpha. We know 1 over LC is equal to omega naught squared, we solve for omega naught. Then everything else becomes the same, okay? So, zeta is equal to alpha over omega naught. What is the value of zeta? .0316. Okay, question. Well, that doesn't seem right. There's no way. What? No. How do you divide 1 by 316 and get 316? That's just wrong. That was an accident.
So, is the calculator wrong then?
Yes. All of your calculators are made by the man. You know that, right?
Aren't you the man?
All right, well, we'll keep going. It's ridiculous. It's like they multiply by each other, and it's the same number if you divide by them. It's not quite. I mean, it's like 10 times different, but what the heck? Yeah, it's like you multiply them and then multiply by 10, and then you get the number. That's why I'm like, you know what? I'm sorry for questioning you. Thank you for standing up for him. I hate both of you now. So the question we now have to answer is this overdamped, underdamped, or critically damped? Why did you say underdamped?
Less than 1.
Yeah, in order to make this underdamped, this value has to be less than 1. Okay? In an underdamped system, what it means is that the system reaches the steady state value very quickly, but then it experiences an overshoot, which causes it to then have to correct, and it oscillates about that point until it eventually reaches equilibrium. Okay? That is the statement of an underdamped system. We also know that the math gets super gross, but it is what it is. So let me go grab my textbook because I need to make sure I tell you these equations right. Yeah, I've already done that enough. Ooh, Y-Y connection. Ah, gross. Ah, so gross. Okay. What we're going to go ahead and solve for here is we know that the equation for S, regardless of what system it is going to take the form of negative alpha plus or minus square root of alpha squared minus omega naught squared. Okay? The whole reason why we put this into this format is so that the solution method for the rest of the problem is the same. That's the nice thing about doing it this way. It takes an extra step, but it makes things so much simpler. Okay? We know what alpha is. We know what omega naught squared is. We're good. We also know that omega naught is larger than alpha because zeta is less than 1. For that reason, that makes it an underdamped system. Because it's an underdamped system, this has an I that comes out of it. So what we're going to solve for is what's called the natural frequency. The natural frequency is omega n. Omega n is the frequency at which it oscillates after overshooting. And that is equal to the square root of omega naught squared minus alpha squared. You'll notice that this is just the reverse of that, which means this is a positive number, and that is not. This one does not have an I in it. That one does. This one's an equation, and so is that one. Math. Okay. But now that we know all of this about our system, I mean, we've just solved for omega n. We don't need to solve for S here. That's one of the nice things about an underdamped system is we don't even need to solve for S. We know what S is. We don't even need to know it because we have fun equations that the book gives us that we can use. The solution to this problem, which is step 4, estimate a solution. The solution is going to be equal to, we know IL is equal to IL comma C plus IL comma P. You got your complementary solution plus your particular solution. Okay? That's what we've done this whole time. Complementary solution goes away. The particular solution is your steady state solution. Did everybody hand in their test? Did you guys hand in your quiz? Or are you waiting till after class? You're waiting? Okay. And I probably won't give a spoiler alert on what the answer was. Terrible. But this is your particular solution. Your particular solution is your long-term solution. This is long-term plus transient. This is part that changes plus part that stays around. Okay? That's how we define this. There is a small piece that exists for a short amount of time that changes. There is a large piece that persists indefinitely. And that is our solution. Okay? So here, ILC, which is the transient part that only stays around for a little bit of time, the solution for it has the form that's given in your book, which is super fun, which is A1 e to the negative alpha t times cosine. I need more board space. I have sadness. I'm going to go right over there. So, oh, hey. Goodbye. So, okay, I'm just going to rewrite this piece here. IL is equal to IL comma C plus IL comma P, just rewriting. We know IL comma C is equal to the equation given to your book, which is A1 e to the negative alpha t times cosine of omega n times t. Plus A2 e to the negative alpha t times sine of omega n t. Okay? And the whole reason why we get a cosine and a sine out of here is because anytime you have e to the I omega t, that's going to be equal to cosine of omega t plus I sine omega t. And it's just this is Euler's formula. That's why we end up with a cosine and sine function. Okay? But I guess you don't really need to know that right now. I'm just trying to explain how come this formula looks so different. It's still an exponential function. It's just an oscillating exponential function. Okay, so that's the complementary solution. And then we have our particular solution, which is equal to A3. Because this has the same time form as this, which is a constant. Okay? Well, step 5 is solve for S. Guess what? We've already solved for alpha. Done. Step 6 is solve for your particular solution. To do that, we have to use the non-homogeneous equation. Okay? So what is the non-homogeneous equation? Yes, it's just the constitutive equation. It's this thing. Okay? So we go ahead and we plug in this nasty thing into that. And we solve it at t equals 0. So that's gross. All right, let's do it. Whew. Sickness. Disgust. Okay. We've got Vs over RLC is equal to d squared IL over dt squared plus 2 alpha dIL over dt plus omega naught squared times IL. Okay? That's our constitutive equation. Now here, we exchange our constitutive equation for our particular solution. So we've got d squared IL comma p over dt squared plus 2 alpha dIL comma p over dt plus omega naught squared ILP. Now we're going to write that friggin' giant thing. This thing. How do we do that? It's just massive. I don't even want to calculate the second derivative of that thing. Does anybody know what the first derivative is? Anybody want to take a stab at it? Huh? It would just be what? A3, what? It's just 0. So this becomes Vs over RLC equals d squared over dt squared A3 plus 2 alpha times d over dt of A3 plus omega naught squared times A3. Okay. So what is the second derivative of A3? That one's a 0. Probably got abandoned by its parents. Started doing drugs early on in life. Clearly a 0. What is the first derivative of A3? Also a 0. Boy, just a bad family. The only one who's not a 0 is this one over here. You guys think it's funny, but I mean, that guy's threw away his life. Don't smoke crack. Don't worry, I posted on YouTube. Yeah. I really need to find better hobbies. Not than smoking crack. Yeah, actually, there's a running joke in my family that I am the most drug illiterate person I know. Like, I would go up to my brother like, hey man, what are you doing? Are you smoking a line of weed? And he's like, that's not how it works. I'm like, are you sniffing it? Like, no, you don't do it in lines. And then he makes fun of me, and I'm like, well, I didn't even hang out with people who did drugs. I mean, it takes a lot to even make me drink caffeine, although I do it every Tuesday and Thursday, because this class is murder. All right, so Vs over RLC is equal to omega naught squared times A3. Okay, we know that omega naught squared is equal to 1 over LC. So you know what? I'm just going to go ahead and plug that in. So this is equal to A3 over LC. Well, guess what? We've got an LC here. We've got an LC here. These kind of cancel out. So if we multiply both sides by LC, we get A3 is equal to Vs over R, which is equal to 24 divided by 50, which is equal to 0.48. And the units on A3 is amps. Yes?
I didn't understand why you didn't cancel the last one. Because the first one is 0, the second one is 0.
Yes, this is because this one came from a broken home. This one didn't go to school. No, it's the derivative of a constant is 0. The derivative of 0 is 0. But this is still a constant.
Okay.
So it's this, its derivative is equal to 0, and the derivative of 0 is also 0. So that's why we didn't cancel the first one. We are not going to see that happen very soon. Because guess what? We're getting into variable voltage sources very quickly. Okay, so we got this. We've solved for A3. Step 7 is initial conditions. If we assume VC equals 0 and IL equals 0 at t equals 0, which I didn't write, but if we assume that, then we can plug that into your overall equation and solve for A1 and A2. Okay? So here, I'm going to take this initial equation because we solved for IL. Aren't you cold, Jonathan?
I am cold. I should order a sweater.
Do you want to borrow my coat?
No, it's okay. I'm leaving in 4 minutes.
What do you have? 4 minutes. So important.
I'm being stabbed by a needle.
Yes. Somebody's going to go stab him. He's gonna get shot.
So I missed my opportunity.
Yeah, are you the second derivative? You're getting drugs, you're gonna be shot. I mean, come back to class next week, please, so that you don't turn out like the first derivative.
We'll see on Tuesday.
That's true. That's true. Oh, it's so bad. Ah.
That's gonna be tough all 3 days.
Oh,
That is kind of tough. Right before Easter. Good luck, man.
hopefully I survive.
Hopefully.
Oh no.
But I mean, if you do turn out like first derivative, I'll keep mentioning you in my classes.
I'll go to your funeral, maybe.
You're carrying my casket.
You got to do the death dance. Dun, 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 dun,
Sit there clapping.
I'll give a heartfelt speech. I'll bring pie.
So he was pretty mediocre and all the time.
I remember Jonathan well. I still can't pronounce his last name.
Probably never will.
Probably never will. He was a good kid, except for that part where he handed in his portfolio and it looked like trash.
I haven't handed it in yet.
Ah, good call. There you go. Don't. Just don't. That's true. Just be waiting indefinitely. All right, so let's at least try to finish this. Okay, so we got our overall solution. IL is equal to ILC plus ILP. We'll go ahead and throw in what the values of ILC and ILP are, which is just combining these two. So we have A1 e to the negative alpha t cosine omega n t plus A2 e to the negative alpha t times sine omega n t plus A3, where this is your complementary solution and this is your particular solution. Little guy, you so cute. You so cute. Who's my cute little equation? The awkward laughing is appropriate. Is he okay? I don't know. I'm teaching circuits and I might be clinically insane at this point.
I mean, it sounds like everything going to your brain.
It's fair, it's fair. Okay, so I'm going to plug in my initial conditions. What initial condition can I plug into this one? We know A3, we know alpha, we know omega n. If we pick a time for t and we pick a value for IL, we're good. Do we have a time for t and a value for IL? Yes, we know at 0 it's equal to 0. So I'm going to go ahead and say a 0 is equal to A1 e to the 0 times cosine of 0 plus A2 e to the 0 times sine of 0 plus A3. What is e to the 0? So that's just gonna basically, I mean, it's multiplying, it's gonna disappear because e to the 0 is just 1. What is cosine of 0? What is sine of 0? Which means this one goes away. Huh? Probably. Actually, this one was probably hanging out with this guy. I know, right? Aren't you supposed to be getting drugs right now? I'm sorry. I think these lectures are on YouTube, so you can go back and you know what? You may not want to, for your own sanity. Watch the next one though.
Yeah, he's gonna roast me the rest of the video while I'm gone.
Yeah, we lost one of our own today. He's out there doing drugs, getting shot. on the streets. He was a mediocre individual.
Thanks. I'll see you on Tuesday, maybe.
Maybe. Have a good weekend. Okay, so we know that 0 is equal to A1 plus A3, which means that A1 is equal to negative A3. That's nice. That's nice. And that's equal to oh, thank you. Negative Vs over R, which is equal to 0.48. Ooh. I'm amused by the little things in life. My mom says I'm special, but she also says I'm a first derivative of a constant. So,
Is it a 0.48 negative?
yes. Yes, it is. Thank you. Because, yeah, it's a negative of a positive, so, yeah. Okay, so we solved for A1. We're halfway there. Oh! Yeah, no, we're halfway to solving what A2 is. We're almost there. We're really close, and then this is done. So our A2, second condition is we know VC is equal to 0. Okay? VC is equal to VL from our component equations. So if we go back, initial equation, we know VC of 0 is equal to 0. Okay? We know VL of 0 is equal to 0 because VL equals VC. That's this equation. So whatever initial condition applies to VC, well, also happens to apply to VL. Okay? Now we know the equation for VL is equal to L DIL dt. So L DIL dt of 0, where, well, L times DIL of 0 of dt is equal to 0. So if we calculate L times the derivative of this, we should get 0. So we know L times derivative of this, which is what's the derivative of ooh, gross. That's disgusting. I don't really want to solve that. You know what? It's just the derivative of that. Let's go ahead and have a break. I'll see you in 10 minutes.